In this screencast, we're going to introduce probability. And just a very small introduction, just a little bit we'll need for statistics. Why do we need any for statistics? Isn't statistics all about analyzing data to make decisions? Why should we care about probability? The best way to see this is to look at an example. So a large restaurant chain has a high employee turnover rate, 55% a year. Each year they lose 55% of their employees. So that's really expensive in terms of hiring and training costs, employee morale. This is not good. They'd love to get it down. So at a random sample of their restaurants, they increase the pay by 50 cents an hour, and they also increase employee control over their shift schedules. So this is an experiment. They're imposing a treatment on a random sample of their restaurants to see if things are any better after the treatment. And at those restaurants in the next year, the turnover rate is only 42%. Well, that's a big improvement. The cost of the changes would be worth it, even with the increased pay, if the turnover really decreased to 42% nationwide, if those changes really had an effect. But that 42% was just in a small sample of the restaurants. Maybe it was just random chance. Maybe those stores would have had a 42% turnover rate without the changes. So maybe the additional pay and the employee control had nothing to do with the improved turnover rate. We know that association does not imply causation after all. It might have been because of the treatment, because of the pay and control, and it might have just been random chance. How did they decide? Well, they decide by turning it into a probability question. They ask this question: if the added pay and control had no effect, so if the changes they made were worthless, what's the probability that just by random chance they would have had a turnover rate of 42% or lower at those stores? How surprising would the data be that they got? How surprising would the results be if the changes they made didn't cause anything? If the changes have no effect, what's the probability of getting the data that they got? Now we'll see how to answer questions like this later, but that's why we need to understand probability a little bit. If they could say that it would be very, very, very surprising to get a lower rate of 42% just by random chance, then it was probably the increased pay and control over schedules that they gave employees, and therefore they should do it on a national scale. On the other hand, if they say, hey, wait a minute, if the changes we made had no effect whatsoever, there's still a pretty good chance we would have had 42% at these stores just because it was a small sample and just by the random variation that happens everywhere, then that wouldn't give them much confidence that the measures they imposed had much effect. So they're trying to answer a probability question. If increased pay and shift control are worthless, would we be very surprised to see 42% or lower just by random chance? That's what they want to know. And we'll see how that plays out later, but that's a motivation for trying to understand at least a little bit about probability. So some very basics. If you flip a coin, what's the probability that it comes up heads? 50%, you knew that. There's two things that could happen. You could get heads and tails. They're equally likely, so it's 1/2 each of 50%. Probability is always a number between 0 and 1, and it tells us the proportion of times a particular outcome would happen if an experiment were repeated many times. So if you flip a coin 100 times, you may not get exactly 50 heads, but the more times you flip it, the closer the running proportion of heads comes to 50%. So maybe you flip it 100 times, maybe you don't have exactly 50% heads, but it's probably pretty close. And it's even closer if you flip a coin 1,000 times. If you roll an ordinary 6-sided die, by the way, die is singular of dice, those things you roll in a kid's game. I've had students who second language was, whose first language was not English, and they didn't know what the word die meant. So it's just a singular of dice. Anyway, if you roll an ordinary 6-sided die, what's the probability that you roll a 1? Well, 1/6. A die could come up 1, 2, 3, 4, 5, or 6. They're all equally likely, so it's 1/6. So what's the probability that you don't roll a 1? Well, 5/6. So that's a general rule. The probability of something does not happen is 1 minus the probability that it does. If I tell you there's a 20% chance of rain tomorrow, then you know there's an 80% chance it doesn't rain. And by the way, the fancy way we write this in mathematics is this. This is pronounced probability, or P of not A, probability that something doesn't happen, is 1 minus P of A, 1 minus the probability that it does. So that's just a fancy way of writing in math. You don't have to worry too much about that. Okay, how about this? A deck of cards. So this is an ordinary playing cards, has 4 suits: clubs, hearts, diamonds, and spades. And each suit has 13 ranks: 2, 3, 4, 5, 6, 7, 8, 9, 10, jack, queen, king, ace. That's what cards look like. So if you pick a card at random, what's the probability that you picked a heart? Well, 13 out of 52, 1/4 of the cards, or 13 of the cards are hearts. What's the probability that you picked an ace? Well, 4 out of 52. There's an ace of clubs, hearts, diamonds, and spades. What's the probability that you pick a heart or an ace? Well, 16 out of 52. And here's a typo, but that's supposed to be heart. Anyway, 16 out of 52. There are 13 hearts and then 3 additional aces. You don't count the ace of hearts all over again, but there's got 13 hearts total, 3 aces that aren't hearts, and so that's a total of 16 out of 52. And the rule that's going on here is that the probability of A or B happening is the probability of A plus the probability of B minus the probability of A and B. So if you take this 13 out of 52 and add the 4 out of 52, that's 17 out of 52, but you've double counted the ace of hearts, so you have to subtract off the probability that it's an ace or that it's hearts and an ace. You have to subtract off 1 out of 52, and that's where the 16 comes from. That's a way of thinking about it. So a rule is probability of A or B is the probability of A plus the probability of B minus the probability of A and B. So here's another example of that. Suppose you have a class with 40 students, 30 women, 10 men. Of the women, 9 are business majors and 21 are computer majors. Of the men, 5 are business majors and 5 are computer majors. So if you pick a student at random, what's the probability that the student is a woman? Well, 30 women, 40 students, 30 out of 40. What's the probability that the student is a business major? Well, you've got the 9 women business majors and the 5 men business majors, so that's a total of 14 out of 40. What's the probability that the student is a woman or a business major? Well, you've got 30 out of 40 that are women, the 14 out of 40 that are business majors, so you add those two together. Now, if you stopped there, you'd have 44 out of 40, which makes no sense. But you have to subtract off the 9 out of 40 who are women business majors that you've already counted amongst the women. And you got a total of 35 out of 40. And if you look at my numbers, that should make sense. 30 are women, 5 more business majors, namely the 5 men, and so that's a total of 35 out of 40 are women or business majors. So again, a rule is P of A or B is the probability that A happens plus the probability that B happens minus the probability that they both happen. Now, what about AND events? Well, we're going to just look at a very special case where the events are called independent. And that means they have no effect on each other. And let's just see with an example. If you flip a coin 3 times, what's the probability that you get heads on the first flip and the second flip and the third flip? And the answer is 1/2 times 1/2 times 1/2, or 1/8. The rule is that if A and B are independent, if they have no effect on each other, then the probability of A and B is the probability of A times the probability of B. And let's see why this makes sense. If you had 800 people flip a coin 3 times, about 400 of them would get heads on the first flip. About 200 of those would get heads the second time they flipped, and about 100 of those would get heads on the third time they flipped. So about 100 of the original 800, or 1/8, would get heads all 3 times. And that's what rule predicted, 1/2 times 1/2 times 1/2, which is 1/8. So let's see another example. If you roll a die 4 times, what's the probability that you roll a 1 all 4 times? That means you got a 1 on the first roll, and on the second roll, and on the third roll, and on the fourth roll. And the rolls are independent. The die doesn't care what happened the first 2 times when you roll it the third time. So we can use our rule and just multiply. 1/6 times 1/6 times 1/6 times 1/6, which is 1 out of 1,296. Very small chance of getting a 1 all 4 times. which is what we'd expect. Or another example, you roll a die and then you flip a coin. What's the probability of rolling a 1 and then flipping a head? Well, there's a 1/6 chance that that the die was a 1 and a 1/2 chance that the coin was a head. So 1/6 times 1/2 or 1/12. So again, the rule is if A and B are independent, if they have nothing to do with each other, then you can find the probability they both happen by multiplying the probabilities. And as an example of what can go wrong when they're not independent, if you flip a coin once, what's the probability that you got heads and tails? Well, 0. If you flip a coin once, either you got heads or you got tails, but you can't get both. So it's not 1/2 times 1/2, which is equal to 1/4, it's just 0. So a rule, P of A and B equals P of A times P of B, this rule here, that works when A and B are independent. Independent means they have no effect on each other. They just have nothing to do with each other. One happens, the other one can happen or not happen. Another example. If you suppose you know that 95% of people are right-handed. I think that number's a little high, but let's just go with it. If you suppose you know 95% of people are right-handed. If you pick 4 people at random, what's the probability that all 4 are right-handed? Well, if you pick 4 people at random, then they're independent, so it's just 0.95, 95% times 0.95 times 0.95 times 0.95, which turns out to be 0.81. Again, our multiplication rule, we just multiply the probabilities. What would be the probability that at least one of them is not right-handed? Well, if there's an 81% chance, or 0.81, that they're all 4 right-handed, then the other 19% of the time, 0.19, must be the chances that at least one of them is not right-handed. That's an important example, and we'll see why later in the course. Here's another example of that. Suppose 99% of people are free of the gene for RD syndrome. RD stands for rare disease, something I just made up. If you choose 30 of them at random, 30 people at random, what's the probability that all 30 are free of the gene? Well, you multiply 0.9 times 0.9 times 0.9 30 times. That's 0.99 times 0.99 times 0.99 30 times. That's 0.99 to the 30th power, which is 0.74. So there's a 74 chance that all 30 people are free of the gene. And then again, that means that there's a 26% chance, 1 minus 0.74, that at least one of them does have the gene. So these two are important examples, and we'll see why later. So there's a whole lot more going on with probability, and we'll see a little bit more in homework and in the class, but these basics will help you get started. Edgewood does have a semester-long course in probability, which we really won't have time to go into in the small amount of time we have. If you're really interested in probability, you're welcome to take that semester-long course. It does require 2 semesters of calculus as a prerequisite, so maybe you don't have time for that. So I hope this will help give you the very beginnings of probability and that you'll be able to do just fine with the check your understanding.